Welcome! It is time for a challenge. In this problem, we will try to find the electric field of a uniformly charged sphere, right? Charged only in its surface. It's basically just an empty shell, right? I'm going to be basing this off of Griffiths problem 2.7 as it appears in the 4th edition of Griffiths Introduction to Electrodynamics. Now, this problem states the following. It says, find the electric field at distance z from the center of a spherical surface of radius r that carries a uniform charge density sigma. Treat the case, whatever. They're saying we have to find, of course, the electric field inside and outside and express the answers in terms of the total charge of the sphere. Cool. And then they give us a hint that we don't care about. I will show you a very easy way to do this problem. So, as usual, we have to define our coordinates. What's going to be our coordinates, right? That's step number one. Define the coordinates. So we are dealing with a sphere, so of course we have to use spherical coordinates. So for that reason, let us just define them. Let's say that we are going to be interested in some point that's going to be somewhere inside this infinitesimal area, right? That infinitesimal area is going to be what we call the A. And there's going to be a point there that is of interest, so its projection on the xy plane is going to be somewhere here, and thus the angle that this point forms with the x-axis is going to be what we call the angle theta, and then the vector that it forms with the angle z is going to be the vector phi. Now, be very careful. Some people call theta the other way around. Some people say phi to what I call theta. Some people call theta to what I call phi. It doesn't matter. Just be very careful that you understand which one you're using and which one you are seeing, okay? So by using this definition, my coordinate x will simply be the radial distance of the sphere, which is this fixed r, times the cosine of phi times the sine of theta. Y will always be r sine of phi sine of theta, while z will simply be big R times the cosine of theta. Now, by this definition, we'll have that the angles are going to be defined as follows. So theta will be defined between 0 and pi, while phi will be defined between 0 and 2 pi. So, with this, we now have clarity on which coordinates it is that we are using. Okay, you can do it the other way around. You can call theta phi. It doesn't matter, but just make sure that you are going to be consistent with the notation. Okay, so now we go to step 2, which is to write down the electric field. So the electric field formula is 1 over 4 pi epsilon 0, and we integrate our charge density sigma over the entire sphere, this entire surface of the sphere, dA. And of course, we have to consider that we still have this unit vector, right? We have to keep the direction that goes between this point and our point of interest and divide by its magnitude, right? As we are always doing. So what we now need to do is find these three quantities. We need to find the r vector, and we need to find its magnitude and the surface area element. Okay, so how do we find vector r, right? This vector right there. How do we find then the unit vector? That is the most challenging part in this problem, and that is where we will, I will show you something that will make it much easier, because this problem tends to be very hard. I will show you how to make it easy. Now, what is a vector? Just think of that. A vector basically is telling you how do you go from your starting point to your end point. That's basically what it's telling you. So if you start here, how do you go to there? That is what you want to do. So if you're in any point in the sphere, how do you go to point P? Well, regardless of where you are on the sphere, if you walk a negative distance of big R in the radial direction, then you will always get to the center of the sphere, right? That is by definition. If you are here and you walk the radius towards the center, then you will get to the center. Same thing here, same thing there, same thing everywhere. And then once you get to the center, you just need to go z steps upward. And that's it. There you go. It's that easy. So how do we find this row vector that, of course, will be changing every time we go to a different point on the sphere? Well, to find the unit vector, let's begin with the non-unitary vector, right? Which is going to be x in the x direction plus y in the y direction plus z in the z direction. And then to find the unit vector, we will simply divide by its magnitude. So what is this going to be? So let me just maybe quickly move this to the side so I have more space once I plug everything in. So this unit vector rho will be x in the x hat direction, but x is r cosine of phi sine of theta in the x hat direction plus y, which is r sine of phi sine of theta in the y hat direction, and z is r cosine of theta in the zeta direction. And we have to divide all of that by the modulus, which will be each one of those components squared. Okay, so here we get r squared cosine squared of phi sine squared of theta plus r squared sine squared of phi sine squared of theta plus r squared cosine squared of theta. So what do we do here? So we need to factor out r squared, but of course when we take it out of the square root, it's going to be r, right? Where the square goes away. So then of course r squared, r squared, and r squared, they all go away. And now we can factor out sine squared, right? Sine squared of theta, factor of cosine squared of phi plus sine squared of phi, which means that this term, that's the equivalent for this term. But we know that this is 1, right? Cosine squared plus sine squared is 1. So we get sine squared of theta plus cosine squared of theta, which again is also 1. So we end up just with 1 over r. So we can simplify this r with this one, and with this one. So our rho hat vector is simply this. Okay, I was just giving you a quick reminder of how you can find that. So now finally we can plug this in to find our r vector. Not unitary yet. We will find the modulus soon. So this is minus r in the rho hat direction. So cosine phi sine theta in the x hat direction plus sine phi sine theta in the y hat direction plus cosine theta in the z hat direction plus z in the z hat direction. So now let's just basically group everything in the coordinates. So we get minus r cosine phi sine theta in the x hat direction minus r sine of phi sine of theta in the y hat direction minus, okay, and then actually plus z hat, and in the z hat direction we have z minus r cosine of theta. And now we want to find the unitary vector, so we need to divide by the modulus of this. So what is the modulus of that? Well, the modulus of all that is simply taking the square root of each one of these components squared, adding of course. So we get r squared cosine squared of phi sine squared of theta, sorry, plus r squared sine squared of phi sine squared of theta plus, and here we have this squared term, so we get z squared minus 2zr cosine of theta plus r squared cosine squared of theta, and all of this inside of a square root. Okay, now we start simplifying a few things. Just like we did before, we can see that here we can factor out r squared sine squared of theta, which gives us cosine squared of phi plus sine squared of phi, which is simply 1. So instead of having all of this, we simply have r squared sine squared of theta. But look what we have over here. We have r squared cosine squared of theta. So we can factor out r squared, and we get sine squared of theta plus cosine squared of theta, which is of course 1. So instead of having both of these terms, now we simply have r squared. Okay, so we end up with r squared plus z squared minus 2z r cosine theta, which is of course what you would have gotten if you had used the cosine theorem at the beginning. But I think it's good that we do it this way so that we don't have to rely on randomly thinking of a random theorem every now and then. Okay, so now we go for the vector. So the unit vector thus is going to be this amount divided by this. Okay, now let's plug all of this into this. Oh, well, we still need to find dA. So let's find dA quickly. So if we are integrating in a sphere, the unit area element, well, it's simply going to be r squared sine of theta d theta d phi, right? That's simply the area element in spherical coordinates, which you should have seen in your calculus classes before. Okay, so now let's plug all of this into the equation for the electric field. So the electric field will be 1 over 4 pi epsilon 0, and then we integrate both over theta and phi. Theta goes from 0 to pi, phi goes from 0 to 2 pi, and we have to integrate sigma, which we can actually take out of the integral. Now our unit vector, this will give us minus r cosine of phi sine of theta in the x hat direction minus r sine of phi in sine of theta in the y hat direction plus z hat direction times z minus r cosine theta. And all of this we need now to divide by the modulus cubed. So we get r squared plus z squared minus 2zr cosine theta to the 3/2 power. And we still need the dA, which is going to be r squared sine of theta d theta d phi. Okay, so now of course, because of the geometry of the problem, there we go. Because of the geometry of the problem, we know that these two parts will give us 0. Again, I would just show you that. I don't like just saying, oh, this is 0. Because of the geometry, of course, any point on the left-hand side of the sphere will cancel out the lateral, right, in the xy plane contribution of what is on the other side, right? Anything that is in the negative y will cancel out the contribution in the positive y, and in the negative x cancels out in the positive x. So we only have contributions in the z direction. But I will show you where that comes from mathematically. So don't worry. Now there's, of course, 3 different integrals here, right? We have in the x hat direction, in the y hat direction, and in the z direction. So let's go one step at a time. So let's go for the x hat direction first. So that integral is integral from 0 to 2 pi of this integral from 0 to pi minus r cosine of phi sine of theta. I'm leaving the x hat out because we are implying that we're already there, but I guess you could write it down. It doesn't make any difference. R squared plus z squared minus 2zr cosine of theta to the 3/2 r squared sine theta d theta d phi. So looking at this, the theta integral looks very nasty. You have sine squared theta divided by all of this. So it looks nasty. So separating the integrals, we get the phi integral is simply integral from 0 to 2 pi of cosine phi d phi. And then you have everything else. But thankfully, this integral right here is 0, right? That is the sine of phi between 0 and 2 pi. But sine of phi at 2 pi is 0 minus sine at 0, which is also 0. So this part is 0, which means that we are multiplying the other integral by 0, which also gives us 0. So we don't have to worry about any of that. So thus we see that the x contribution does end up cancelling out because of the fact that we are going over the entirety of the sphere. If our limits of integration had been different, that would have been different as well. So this part is 0. Now, of course, in the y case, we have the same situation. We have this sine phi. So in the y direction, we will get integral from 0 to 2 pi of sine phi d phi, which is going to give us minus cosine of phi between 0 and 2 pi, which gives us minus 1, which is also 0. So even though the other integral would have been very, very, very unpleasant, we don't have to worry about it thanks to the fact that one of them is 0. So this part is also 0. So as you can see, things have simplified considerably. So let's now rewrite what we now have. So this is 1 over 4 pi epsilon 0 sigma. And then actually let's separate our integrals because we don't have anything in phi. Notice there is not a single phi here. So this is basically integral from 0 to 2 pi d phi, integral from 0 to pi of, well, now everything else. So here we have the z hat vector, which we can take out. It doesn't depend on any of our angles. Then we have z minus r cosine of theta. The r squared we can also take out. I guess we can put it somewhere over there, r squared. Then we have sine of theta, d theta, and the d phi we already used. And here we have r squared plus z squared minus 2zr cosine of theta to the 3/2. Okay, whew. Now we need to solve these integrals. Now the first one is of course trivial, that's simply 0 to 2 pi. That's nothing particularly interesting, right? This is 1 over 4 pi epsilon 0 times, well, in the z hat direction, sigma r squared times 2 pi. And now comes this integral. So what do we do with this integral? Notice that we have cosine down here, well, cosine, and we have cosine down there, up there. And we have sine here, right? So what we have is basically, we have cosine and its derivative, and cosine again. So it makes sense to try to use a substitution that involves cosine. So my first guess would be to say, okay, let's say u is going to be r squared plus z squared minus 2zr cosine theta, because that way we get rid of what we have down here. And when we do that, we get that du, this is going to be minus 2zr times the derivative of cosine theta, which is minus sine theta. So actually we get another minus sign, which cancels out that minus sign. So sine theta d theta. So now we want to plug all of this in, right? So let's see. Now, I will leave the limits unchanged because it's a bit too annoying. I will just plug them back in by the end of this. So we have z minus r cosine theta. Well, what is cosine theta? Cosine theta we can find from here, right? Cosine theta is simply, let's see, u minus r squared minus z squared, and then we need to divide by 2z and multiply by minus 1. So we actually get minus, these signs are changed, so we get z squared plus r squared minus u. There we go, right? Just double checking, so we have to put that there, r squared plus z squared minus u divided by 2z. By 2zr. Okay, we almost forgot about the r. Good thing we checked. So divided by 2cr. So now let's plug it in. So here we have z. So integral, indefinite integral. Let me take some more space. Indefinite integral of z minus r times cosine theta. Cosine theta is that. The r's cancel out. So we get z squared plus r squared minus u divided by 2z. And then we have sine theta, which we can find from here. So sine theta d theta, this is simply du divided by 2zr. So this is du divided by 2zr, and all of this is divided by u to the 3/2. Now it may not look any better, but we can actually do a lot of things. So First of all, we can take minimum common denominator here. So instead of having just z, we get 2z squared minus all of this. So let's now put it together. The minus goes through, so we get minus z squared minus r squared plus u. So we have 2z squared minus z squared, so simply z squared. Okay, and now we have a lot of constants. We have 2z, 2zr, so we can factor them out. So we get 4z squared r, right? So we get rid of all of these things. And now it's looking a lot better. Whoops, there we go. Okay, so let's now just rewrite it. So our electric field is 1 over 4 pi epsilon 0. I'm keeping all of my constants. I'm not simplifying anything because it may make it easier to later identify like the surface area or something. You could be canceling them out, but I like to keep them there as pets until the problem is solved, and then I'll just simplify and see what the most convenient way of writing it is. Actually, one thing I will simplify is this r. So r and r squared, I will simplify that. Okay, so now we have these integrals. Now let's separate them because z squared and r squared don't depend on u. So we can separate one as z squared minus r squared, integral of u to the minus 3/2 du. And then we have the other integral, which is going to be integral of u du over u to the 3/2, which is of course simply u to the minus 1/2. So this is integral of u to the minus 1/2. And we know how to integrate both of those. So they are very easy integrals to solve. So this integral right here, right, maybe let's just do it here so we can then plug it in. So I1, which is going to be this, that is simply going to be minus 2 u to the minus 1/2, right? Because we take the derivative, minus 1/2 goes down, it cancels this, and we end up with u to the minus 3/2. So that is the first part. And then we have to undo the substitution. So if we undo the substitution, that means that we get minus 2 divided by the square root of u. So divided by the square root of r squared plus z squared minus 2z r cosine theta. There we go. Okay. So now, of course, we still need to evaluate between our endpoints. Now, our endpoints are 0 and pi. So that is the first integral, okay? So, of course, we need to evaluate the endpoints, as I said. So we get minus 2 divided by, and now let's evaluate at the first one. So this is at the first one. So we get r squared plus z squared minus 2zr cosine of pi. But cosine of pi is minus 1, so we get plus 2zr. And then we have minus 2, so we get positive 2, divided by, now the same thing, but with cosine of 0, which is 1. So this time we get minus 2zr. Okay, now what we need to do is take a look at this. What we have in the denominator is exactly something squared, right? This is r plus z squared, right? Simply multiply through, you get exactly the same thing. And on the other side, we have r minus z squared. So this means that we can get rid of our square root, but we have to be a little bit careful because z in principle could be positive or negative. So, you know, we could just, we have to use the absolute value, because in the case where z is negative and has a greater absolute value than r, we have to be careful because otherwise we would have a negative square root. Plus 2, and then we have the absolute value of r minus z. Here, of course, it is more direct. Even if z is positive, then this can be a little bit dangerous. Okay, so this is the most general case. Of course, our example is in the case where z is positive. We clearly defined the point z to be positive. But if you want this to be, valid for any single point in space, you should do it like this, and then you can check for, particular points. Okay, so this integral gives us minus 2 divided by the absolute value of r plus z plus 2 divided by the absolute value of r minus z. There we go. Now let's go for the other integral. So integral número dos. Okay, so this is I2. Now the procedure will be the same basically, right? So that integral, we can, well, evaluate it very quickly. It's u to the minus 1/2. So that has to be 2 u to the 1/2, right? So when you take the derivative, you get 1/2. The 2 cancels out with the 1/2, and there you go. And now we need to undo the substitution. Again, what was the substitution? The substitution was r squared plus z squared minus 2zr cosine of theta. And this thing is evaluated between 0 and pi. So here we have 2, and now let's do it like this. So square root, when we are at pi, we get r squared plus z squared minus 2zr, sorry, plus 2zr, because the cosine of pi is minus 1. And then we have minus the square root of r squared plus z squared minus 2zr, because this time the cosine is simply 1. And just like before, we will now rewrite this as, you know, this perfect square. So we get square root of r plus z squared minus the square root of r minus z squared. And then, well, just as before, we take the square root, so we get the absolute value of r plus z minus the absolute value of r minus z. And now we simply plug this back in. That's our result. So we can see not too bad. So we plug it back in. So we get plus 2 times absolute value of r plus z minus absolute value of r minus z. Okay. Now we can do a few little things to simplify it a little bit further. So let's see, what can we do? Well, first of all, we can factor out the 2's, right? We have 2, 2, 2. So 1, 1. And we can get rid of this 4, which is now a 2. I said this 4, which is now a 2. And I guess we can now go ahead and simplify it with this 2. And it just looks a little bit better. And in principle, this is your result. This is the general electric field. This is the formula for the electric field in any point of space. But of course, it doesn't look good. So now let us take this formula and evaluate the case when we are, for the electric field, when we are outside of the sphere. So when z is greater than the radius, right? So what happens when we are outside of the radius? Okay, so somewhere over here or there. Well, actually, I think we are we are exclusively on this point. So yeah, it has to be somewhere over there or there or there or something like that, right? Somewhere on the z-axis, but greater than the radius. So in that case, and why is this relevant? It is relevant because in this case, the absolute value of z plus r is simply going to be z plus r, and the absolute value of r minus z, this is going to be, if z is greater, this would be negative, so we need to add a negative sign to make up for it. So this would be minus r plus z. Okay, so that is how we do this. So now we have 1 over 4 pi epsilon 0 sigma pi r over z squared. And then we have, let's see, so z squared minus r squared. And then we have this parenthesis right there. So there we have minus 1 over r plus z plus 1 over z minus r. Okay, it doesn't look like we can do much, but we can actually rewrite this as z plus r, z minus r. And now we can actually multiply through. If we multiply through with the first term, this will cancel out that, so we get minus z plus r. And when we multiply the second term, we get plus z plus r. And then we still have the second part, so this is what we get instead of that. So here the z's cancel out, and we get 2r, so we get 2r. And then we have the second part, which is this. There we have plus r plus z minus, and this thing is now minus r plus z. So minus that, we get plus r minus z. So the z's cancel out as well. And we get 4 times r. So, oh, by the way, where's my z hat? I haven't written it down yet. So z hat. So here we get 1 over 4 pi epsilon 0. And now we have 4 pi r squared sigma divided by z squared and z hat. And to notice what we have here, the area, the surface area of a sphere is 4 pi r squared. And the total charge we know is its area times its density, right? It's charge density, what the charge is per unit area. So what we have here is exactly the total charge that is in the entire sphere or an entire shell. And look at this. This is exactly the formula for a point charge. So if you are outside of this spherical shell, then it is basically just a point charge. There is no difference. There is no difference, which is very, very, very interesting. And this is, of course, valid everywhere, because even if you were here, you could have set up your z-axis there, right? Because a sphere is symmetric. So regardless of where you are outside of this shell, it always looks as if there was simply a point charge, which is very interesting. Okay, so now in the case where z is smaller than r, we will have that the absolute value of r plus z will be simply r plus z, and the absolute value of r minus z will also simply be r minus z, because, you know, z is smaller than r, so there's no worries with negative signs. So the electric field will be 1 over 4 pi epsilon 0 times sigma r pi over z squared in the z hat direction. And now let's write this just like before. So that is z plus r, z minus r, and then we have minus 1 over r plus z plus 1 over r minus z. Okay, now do be careful, because here we have r minus z and here we have z minus r. So it's not the same. We need to put a minus sign in front so that we get z minus r there. So z minus r. Now we can multiply through. And when we multiply the first term, this and this cancel out. And we end up with minus z plus r. And when we multiply the second term, this cancels out. And we get minus z minus r. So from here, we get that the r's cancel out this time. And we get minus 2z. So we get minus 2z. And then we have this part right there. So there we have plus r plus z minus r plus z. So again, the r's cancel out. And we end up with 2z, which cancel out the minus 2z. So we end up with 0. So this entire thing is 0, which is also very interesting. Because if you are inside of a spherically charged shell, you will not feel any electric field. Inside of this, there is 0 electric field, which is very, very, very interesting. And we will talk more about that in the future when we go more in depth into this topic. So there it is. I mean, that is the problem. It wasn't all that particularly difficult. We had some annoying integrals, a little bit of algebra, but in the end, if you can find your r vector and you are very careful with your notation, right? Very careful. You have a lot of r's, big R, rho, r vector, r hat, magnitude of r. So be very careful with your notation and just go step by step, and you will see that it's actually a very, very easy problem. So I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you on the next video. Thank you very much for watching.